Welcome. In this video, we're going to do properties of regular languages, and mostly we're going to focus on intersection closure property of regular languages. All right, so let's just review what closed means. A closed means that if you perform and operate, if you have a set, like regular language is a set of languages, and if you perform an operation on members of that set, if that resulting language is also regular, then regular language are closed under that operation. So for example, if you have two regular languages and you take the union of those two regular languages, if that resulting language is regular, then regular languages would be closed under union, which they are. They're closed under these are some of the operations that our regular languages are closed under: union, intersection, complement, reverse, concatenation, star closure, and positive closure. You can use this procedure, which I call procedure Bob, to make a DFA into an NFA with one accepting state. That means one initial state and one accepting state. And you can use this procedure to demonstrate closure properties of languages. One is union. You just do procedure Bob on both languages, and then you can create a single NFA that with lambda transitions to demonstrate that the closure property of union on regular languages. Procedure Bob could also be used for the reverse of a language, for the concatenation of a language, for star closure of a language. So go back and review the other video on how useful procedure Bob can be to simplify showing the closure of some of the operations on regular languages. In this video, we're going to focus on intersection. So in order to do intersection, it's doing procedure Bob is not going to demonstrate a new DFA that is the intersection of two languages. So what we're going to do is we're going to use the cross product of two DFAs to create a new DFA, and then if you have two accepting states in the cross product, then that would be the new accepting state of the intersection of the two languages. You can also use this technique for union, but there are other techniques that can be used for union as well. All right, so let's get started on how we do the cross product of two languages. We have two DFAs here. You can see that the symbols of the alphabet are A and B. The first language is any number of A's followed by an ending in a B. The second language it starts with an A or an AB and then can have any combination of A's and B's after that. So let's review how the transition functions work for DFAs, and then we will do the cross product of the transition functions, and then we will draw our new DFA. All right, so look at our first DFA up here. It has three states: one final state, one initial state. The second DFA has four states: one initial state and one final or accepting state. The transition functions for the first DFA are Q0 with an A, you stay in Q0. Q0 with a B, you move to Q1. Q1 with an A, you move to Q2. Q1 with a B, you go to Q2. And Q2 with an A or a B, you stay in Q2. The second DFA, the transition functions, P0 with an A, you move to P1. P0 with a B, you move to P3. P1 with an A, you go to P3. P1 with a B, you go to P2. P2 with an A or a B, you stay in P2. And P3 with an A or a B, you stay in P3. So now we have all the transition functions for these two DFAs. And what we want to do is we want to do the cross product, or we want to do only the transition functions of accessible states. There are some states we will not get to, so there isn't any reason to do that cross product. If you remember what a cross product is, it would be Q0, P0, Q0, P1, Q0, P2, Q0, P3, Q1, P0, Q1, P1, etc. But we're going to start at our initial state, see where we get from our initial state, see where we get from each of those states, and we're not going to make any unnecessary or inaccessible states in our new DFA. So we're going to start with creating the transition functions. And after we create the transition functions, we will then draw our new DFA. So these are the transition functions that will be in our new DFA. I'm going very quickly because in the next slide, I'm going to go through it one by one very slowly. So let's get started. All right. So our first transition function, we are going to start obviously at our initial state, which is Q0, P0. And from Q0, P0 with an A, you're going to get to Q0, P1. Q0, P0 with a B, you will get to Q1, P3. So now we have started at 0, 0 or Q0, P0, and our next states we're going to worry about are the ones that we've accessed from our initial state. So the next two states we're going to deal with are Q0, P1 and Q1, P3. So let's do Q0, P1 next. Q0, P1 with an A, you're going to get to Q0, P3. Q0, P1 with a B, you're going to get to Q1, P2. Now the next state we're going to deal with is Q1, P3. Q1, P3 with an A, you'll get to Q2, P3. Q1, P3 with a B, you'll get to Q2, P3. The next state we're going to do is Q0, P3. Q0, P3 with an A, you're going to get to Q0, P3. Q0, P3 with a B, you're going to go to Q1, P3. The next state we're going to deal with is Q1, P2. Q1, P2 with an A is Q2, P2. Q1, P2 with a B is also Q2, P2. The next state we're going to do is Q2, P3. Q2, P3 with an A, Q2, P3. Q2, P3 with a B, Q2, P3. Q2, P3 we've already done. It's already an accessible state, so we don't need to make transitions because it's already been done. Q0, P3 has also already been done. Q1, P3 has already been done. The next state we need to do is Q2, P2. So Q2, P2 with an A, we stay in Q2, P2. Q2, P2 with a B, we stay in Q2, P2. So let's see if there are any more accessible states. Q2, P3 is already been done. Q2, P2 has already been done. So there are some states that are not accessible, but we are not going to worry about those because we will never get there. For example, you are never going to get to Q0, P2, I believe. Q0, P2 is not a state we're going to get to, so we don't need to worry about creating that state, just as example. All right, so now this is going to be our new DFA. Our new DFA is going to have 1, 2, 3, 4, 5, 6, 7 states. It's going to have 0, 0, 0, 1, 1, 3, 0, 3, 1, 2, 2, 3, and 2, 2. So we're going to draw that DFA in just a minute. We're just going to remember that in order to decide which ones will be accepting, which ones will not be accepting, for intersection, the only accepting state we have would be Q1, P2, which we do have that state. Q1, P2 will be our accepting state, and Q0, P0 will be our initial state. Q0, P0 will be our initial state, and Q1, P3 will be accepting. Q1, P2 will be accepting, and Q2, P2 will be accepting. Q1, P0 we never get to, I think, and Q1, P1 we never get to. We don't have a Q1, P1, and we don't have a Q0, P2. So we will have 3 accepting states for the union of the two languages, and we will have 1 accepting state in the intersection. All right, so let's draw our new DFA. So we're going to start out with our first initial state, which is 0, 0. Instead of saying Q0, P0, I'm just going to name it 0, 0. 0, 0 with an A, I will get to 0, 1. 0, 0 with a B, I will get to 1, 3. Now we will go to our next one, which is 0, 1. 0, 1 with an A. So just to remind you, we are going here. We have 0, 1. 0, 1 with an A, we will get to 0, 3, and 0, 1 with a B, we will go to 1, 2. The next state we're going to deal with is 1, 3. 1, 3 with an A, we'll go to 2, 3. And with a B, we will also go to 2, 3. Next state, 0, 3. 0, 3. With an A, we will stay in 0, 3. And with a B, we will go back to 1, 3. Now we will do 1, 2, which is this one. 1, 2. With an A, we will go to 2, 2. And with a B, we will also go to 2, 2. Now we will do state 2, 3, which is this one. 2, 3. With an A, we stay in 2, 3 with both an A and a B. We've already done 2, 3. We've already done 0, 3. 1, 3. We've already done 1, 3. 2, 2. We have not done 2, 2 yet, so let's do 2, 2. 2, 2. With an A or B, we stay in 2, 2. We've done 2, 2. We've done 2, 3. 2, 3. 2, 2. 2, 2. So we now have 1, 2, 3, 4, 5, 6, 7 states. We have 7 states in our new DFA, and we haven't worried about any of the inaccessible states. These are all accessible. Just review from 0, 0, 0, 1, 1, 3, 0, 3, 1, 2, 2, 3, and 2, 2. These are the new 7 states of our DFA. So now all we need to do is decide if they are accepting. So decide if they're accepting. Well, with intersection, you can only be accepting if it's accepting in both Q1 and P2. So there's only one accepting state here, and that would be the intersection of the languages. And that would be a language that has the string AB. So if you look at the first one, any number of A's followed by a B is accepting. And in the second one, an A, B followed by any number of A's or B's after that. So the only thing accepting in the intersection of these is actually the string AB. Which makes total sense if you think about it. With union, we have accepting states. Oh, that's it. Oh, well, with the union, we have more accepting states. So you can try and see which those states are accepting for the union of the two languages. So now we're going to talk about a 5-tuple representation of regular languages and their closure properties. So regular languages are closed under union, intersection, concatenation, star closure, and complement. And I just want to demonstrate what that means about the 5-tuple. So let's review what a 5-tuple representation of a DFA is. A 5-tuple representation of a DFA is the set of states, the alphabet, the transition function, the initial state, and the set of final states. So if you take a look at this, we have one DFA where we have our set of states Q, the other one has a set of states P, we have a transition function, we have an initial state, and then of course you have the set of final states, which the initial state is part of the set of states, obviously, and the final states or accepting states are part of the set of states. So if you want to do the complement is going to be as a 5-tuple to represent the complement of the language. You would have your set of states, your alphabet, your transition functions, your same initial state, only your final state would not be the set of final states. It would be the set of states minus the previous set of final states. So changing the 5-tuple representation for the complement is very straightforward. The 5-tuple representation for union is you want to union all of the states along with a new initial state, right? You have a new initial state and you're going to create an NFA, which of course could then be translated into a DFA, but to demonstrate the closure properly, you would create an NFA, so you'd have a union of all the states, a new initial state, the same alphabet, but you would have a new transition functions. You'd have all your transition functions, and your new initial state, R0, would be, you put lambda transitions from your new initial state to your previous initial states, and then your set of final or accepting states would be the union of all of the final or accepting states of the previous, of both of them, the union of both of the set of final states. And the 5-tuple for intersection is quite complicated, but after doing the cross product and the whole exercise that we did, it should be fairly clear to understand what's going on here in this large explanation here. So your set of states is going to be the cross product of the states. Your alphabet is going to be the same. Your transition function is going to be defined a little bit differently, and your final states are going to be a set of states that must be accepting in both of them, like we just did in the exercise. Your initial state will be the combined state of Q0 and P0. Your final state would be the combined states of QI and PJ, as long as they're accepting in both of your DFAs. Like we just showed in the last one, it must be accepting in both in order to be a final state. And then the transition functions are going to be the combinations from the combined states. So with an A, you're going to go to the combined state. And so if you take a look at this, this is exactly what we just did, only it's written out as the new 5-tuple and the explanation for the intersection of two regular languages, and regular languages are closed under these operations.